Hello and welcome to another activereach technical tutorial video. Today we're going to have a look at Eigrp, another routing protocol which can help manage routes on our network and help ensure traffic flow is efficient across the network. So Eigrp is a Cisco proprietary routing protocol, and it's sometimes referred to as a dual routing protocol in the sense that it's a distance vector protocol as well as a link state protocol. So we're going to use the same topology we used from our OSPF lab, which are three routers connected to each other. We've got three loopback addresses, one configured on each router, and at the moment there's no routing set up on these devices. So if we have a look at our routing table on router 1, we can see we've got no path to get to 2.2.2.2 on the router 2 and no path to get to 3.3.3.3 on router 3. Although physically there are two ways we can get to those addresses from router 1, down this link or down this link, but we're going to let Eigrp figure out that hard work for us. So to configure Eigrp, it's very similar to how to configure OSPF. We're going to go into global configuration mode, and we are going to turn on Eigrp with the router command. So if you have a look, you can see in here we've got router OSPF or router RIP, and we've also got Eigrp. So we're going to do Eigrp, and first thing we need to do is give it a autonomous system number, an AS number. And this, unlike on OSPF, this has to match across all of our routers that are communicating with each other via Eigrp. So we're going to give it the AS number 100, and we need to tell Eigrp about all the routes that we wish to advertise. So let's just do a show IP int brief and just have a look and see what we want to advertise. We want to advertise the link via our 00 interface, the link via 01, and our loopback. So first of all, I'm just going to turn off auto summary just to stop our routing table from summarizing the networks that we put in there. So I'm going to do that with a no auto summary, and then we're going to configure each network. So let's do 1.1.1.0, and we're using a wildcast mask, like so, and then we want to also do 10.1.1.0, and we also want to do 10.3.3. So there's all of our networks in there, and then we're going to jump across to router 2, and we're going to do the same thing on router 2. There's our interfaces configured. Go into configuration mode, router Eigrp 100, and we're going to turn off auto summary here as well. Add our networks. Like so. And now we can see immediately here, when we configured the network between routers 1 and 2, when those two routers were able to communicate on the Eigrp, they have formed a neighbor adjacency. And that's a good sign. And we can see there our neighbor adjacency has been formed. So we can probably already communicate with router 1. Indeed we can. And if we have a look at the routing table here on router 2, we can see that it's found this route to 1.1.1 via that router, via 10.1.1.1. Having a look at our topology, you can see that it's able to now reach 1.1.1.1 via 10.1.1.1, this direction here. Okay, so let's go ahead and configure router 3 as well. Turn off auto summary, and we're going to do 10.3.3.0. Neighbor adjacency is formed there, which is good. 10.2 and 3.3.3.0. There we go. So we now should have full connectivity between our routers. There we go, and we can see there's a path here which has been found to 1111 and 2222. So we should be able to ping all of our routers. And we can, which is fantastic. So we have full routing connectivity very quickly there, configuring Eigrp. But I just want to have a closer look at what's happening with Eigrp. We know that it's worked here. And we also know that we've got these backup routes in place. So if this link here between router 1 and 2 were to go down, then we'll still have a route to all of our networks via the other path. So how does Eigrp take advantage of these redundant links? How does it calculate these redundant links, should I say? So if we have a look at our Eigrp topology, by doing a show IP Eigrp topology, we can see a little bit more information about how it's found its routes to these connected networks. And we can see here it's got, for example, this link here, 10220. 10220 is found here. We're on router 1 looking at this IP. So we can get to that by going down here and then through the router into there, or by going down this link and down this link. And according to Eigrp, the cost or the work required to get to that link is the same if we go via router 2 on 10.1.1.2 down here, as it is to do it via 10.3.3.1, which is router 3 down this way. So it's calculated here the feasible distance to get to that address, or to get to that subnet, is 30720, and it's the same no matter which path it takes. So in the Eigrp topology, it lists both of those, and one of these will be well, it's got two successors because they are both of equal cost. If one was slightly less than the other one, or slightly more than the other one, should I say, then it might be a feasible successor. But here we've got an equal cost to get to that address, and in the routing table you should see two entries, and the Eigrp will also, or in fact any routing protocol will, but if there's an equal cost to get to two locations, then it will load balance across those two paths. But it doesn't show us in here anywhere about the other ways to get to the 2 network or the 3 network. But you can see that if you do a show IP Eigrp topology all links. So it's not necessary for Eigrp to enter this into its main topology table because it's not needed at this early stage. But you can see here on this router, it's actually got 2 routes to get to 2 routes to get to 2222, one via 10.1.1.2 and one via 10.3.3.1. And what these numbers here are showing you is the feasible distance of this router to get to that network. And the feasible distance is 156.160 via this route, or 158.720 via this route. So of course it's going to pick the winner, which is 156.160. So that's the one that ends up in the routing table. And the other one is got its feasible distance to it The next figure you see here is the advertised distance, or the reported distance from the previous router. So this router has advertised this distance to router 1, and that's where it calculates its feasible distance from. Now if the reported distance from a router is less than the feasible distance that is found, then it will have that as a feasible successor within Eigrp. But if not, then it won't use that route, unless of course it has to if the link goes down. So we'll see the same information has been found on the topology table for router 2. So here if we look at the routing table, we can see we've got our routes to 1.1.1.1, 3.3.3.3, and we've got our two routes the same, because I've left all the costs here as the defaults, and it's basically just a fast Ethernet network. So everything's the same, all the links are the same. And if we have a look at the Eigrp all links, so show IP Eigrp topology all links, all the calculated links here, again from router 2 we've got two paths to get to 1.1.1.1, and we've got two paths to get to 3.3.3.3, and we'll see the same thing on router 3. Two paths to get to 1.1.1.1 and two paths to get to 2.2.2.2. Now sometimes you might see that it hasn't calculated all the paths if split horizon has stopped it. So if split horizon's in play, which it is by default on the Eigrp, then sometimes a route might not be learned, and you might need to disable split horizon on an interface. So it's worth doing some research on that if you're not sure why all of your routes are appearing. So let's say, for example, we want to change the routing on our, because we don't know, we might not know which is the fastest route here. If we were to slow down this link between 1 and 2, then Eigrp should be able to calculate the faster route. So let's go ahead and do that on between routers 1 and 2. If we go on to the connected interface, in configuration mode, and go into interface 00, Eigrp has a metric which looks at the bandwidth, the delay, the reliability, and some other things to calculate the cost of getting somewhere. So if we turn the bandwidth right down on this interface and then do the same on router 2, and on router 2 it's fast Ethernet 00, I think. This one here, which is, I think it's 00, let me just check. Fast Ethernet 00, 10.1.1.2, yeah, 10.1.1.2 is the one facing that way, which is this one here. And we're going to turn that down to bandwidth 10 as well. And I'm just going to jump back onto router 1 to have a look and see what's happened there. So what we've done is we've turned this from a 100 megabits a second, which is default speed, right down to 10. So now let's have a look at the routing table on router 1. So you can see here now the path to get to 2222 is via 10.3.3.1. It now prefers from here to get to 2222 is prefers to go down here. This has been calculated as a faster route than this path down here. So you can see how the bandwidth has affected the Eigrp calculation, and we can see some more information in the show IP Eigrp topology, except this time we've actually got, for 2222 here, we've got one successor, which is via this path here, and we've also got a feasible successor, where you can see the feasible distance is much greater, but the reported distance, or the advertised distance from this router, is lower than the feasible distance. So it's now got it listed in the topology table as a feasible successor. And the advantage with that is the convergence time when a link goes down will be much faster. I mean, okay, we are talking, milliseconds, seconds, probably the difference between, 2 seconds or 1 second in real life. But, in big networks, that can be a very, very important thing. And, live production networks where you've got lots of very important traffic flowing about, the idea of having a very, very fast failover mechanism is very, very important in this day and age. And so this just demonstrates how EIGRP intelligently, or I say intelligently, is manipulated by the network administrator. So as the network admin, you have to make sure your interfaces are configured properly, your networks are configured properly, and make sure you understand how EIGRP has made its calculations to make sure that for your network environment is correct and running efficiently. But here we can see we've got full connectivity between these networks from each router, with no issues, and all of these routes have been configured using EIGRP. So just from router 3 we can reach router 1, we can reach router 2, and again if you have a look at the routing table we can see that the path to router 2 is actually going this way from router 3. On router 2, the path to router 1 from router 2 to router 1 goes via 10222, which is this way, which is faster than that path there. You can also have with EIGRP you can have unequal load balancing as well. So if you've got if we just put our configuration back to normal again, so it was fast Ethernet 00, and on this one it was I'll just take a while to reset. You can see there the path is still going via router 3. There you go, now it's changed. You can see the change happening there just in a few moments. So you can see here you've got this this path to this IP with equal cost. And like I said, EIGRP will load balance on an equal cost path. The other cool thing about EIGRP is you can have unequal load balancing. So if you have two paths with an unequal cost, you can actually set up different variants within the EIGRP configuration. If you have a look here, with the autonomous system number, you can use this variance option to actually have unequal cost load balancing, which can be useful if you've got two paths which are perfectly good, one faster than the other, but you might want to say send 40% of the traffic down one link and 60% down the other link. You can use the variance command there to make sure that some traffic still uses a perfectly good route but by default it will only ever use the fastest. So there's some very, very cool tips there and how you can take this further. But that's covered the basic EIGRP commands, basic EIGRP troubleshooting, and having a look at the EIGRP topology and how deploying EIGRP in your network can maybe help manage your routes and make your network more efficient. Well, I hope that's been useful to you, and thank you very much for watching.